Hi, in this video I'm going to take you through the real basics of map skills for advanced higher geography, and obviously in the videos after that we'll get into the more of the nitty gritty. So the main skills that you need are basic drawing skills, basic scale skills, grid referencing skills, and then we can build towards using those to do some example questions. The main things you want to get out of this is to be quite confident with labeling and drawing, and in the main areas of interpretation and evaluation. So you obviously need to use grid references very confidently, and really the purpose of this video is not to go through exactly how to do a grid reference, but more to point out that six-figure grid references are used for identifying specific features. A four-figure grid reference is used for identifying a larger area, for example a forested area. And you can make clever use of the Eastings and Northings. Those are the blue lines that make up the grid of your map, as those can quickly allow you to section off areas of the map. In other words, you can say to the north of Northing 55, for example, and to the east of Easting 82. And this allows you to quickly divide up the map if you're looking to make very broad observations. The scale of your map is at the current time a 1 to 25,000 map. This means, and you want to take notes here, the scale can be calculated in a number of different ways. Different teachers and different pupils all have differing methods of doing this, but what I've written on the screen here simplifies this if you are not confident at the mathematics of working out scales. Each box on the map is 1,000 meters across, or a kilometer. That is equivalent to 4 centimeters. Therefore, the following statements must be true. And by learning these conversions, you can more quickly draw shapes on tracing overlays and judge distances accurately. So these conversions are absolutely crucial. You'll also need to make use of contours which show the shape of the land, aspect of the slope, and the altitude. Okay, so let's look at grid references first of all. I've mentioned Eastings. These are the blue lines that you see working their way eastwards across the map. You can see 41, 42 and 43. And you can see these are Northings. The fact that they have the same values is just purely coincidental. They work their ways northwards up the map. And they're a very useful way of being able to quickly section off areas. Scale is absolutely essential to your map work. As I was mentioning, each box is 1,000 by 1,000 meters, or a kilometer by a kilometer. You will have to draw shapes onto the map to indicate where you would put different land uses or land use projects. You will need to convert from meters into millimeters. To do this, there are a number of different methods. The one that I prefer is to do distance in meters divided by the scale of the map times by 1,000. That will give you the answer you're looking for in millimeters when you draw it on a tracing overlay or on a piece of paper. So that's the distance you're looking for in reality, the real life distance of the project. Say it's 250 meters long. You divide that by the scale of the map, which we know is always 25,000, and you times that by 1,000, and that will give you a distance of 10 millimeters, which is 250 meters. Here's another way of doing it for the less maths inclined. If 50 meters equals 2 millimeters, then just add up blocks of 2 millimeters until you get to 250. You can count them off on your fingers. 50, 100, 150, 200, 250 is 5 fingers. If each of my fingers is worth 2 millimeters, then that's 10 millimeters in total. However you do it, you have to be confident and comfortable converting real life distances into millimeters on the page, because you will have to draw shapes to scale. When drawing a route, a little bit more judgment is required. Often the distances are quite long, so they'll often ask for a 14 kilometer route or something like that. And in that case, simply knowing that 40 millimeters or one full box width on the map is 1,000 meters, i.e. 4 centimeters equals 1 kilometer, is pretty much all you need to know, and you can judge it from there. As I said, you you'll need to draw shapes on the map. That's roughly, with some distortion, I'm sure, according to what your screen ratio looks like, that's roughly what a 500 by 500 box would look like, a 250 meter by 250 meter box. Sometimes they may ask you to draw funny shapes like rectangles, and I think it's important to note this. The shapes you draw do not have to fit within the grid square. That's quite a common temptation. They can lie across the eastings and northings of grid squares. Here are some practice examples to do, and review the notes that I've just gone through to make sure you're getting these right. It is an essential skill worth 2 or 3 marks to you in your exam. And remember, that's 2 or 3 marks out of 50, so it's quite a significant amount. Okay, on to contours and relief. Contours, as you should be aware, are lines that join points of equal height on a map. They help us to show the shape of the land, the aspect of a slope, and the gradient of a slope. When we refer to the word relief, we're really referring to all of these things: the shapeness, the steepness, the ruggedness and hilliness of the land, and the contours allow us to make observations about that. So for example, on this map you can see that we have some contours. The first thing to take into account is that some contours are thin and some contours are thick. Here you can see the thicker contour has the number on it, 125 metres above sea level. From this we can work out that the divisions between the contours are 125, 130, 135, 140, 145, 150. They are in 5 metre intervals, and that's the first thing that you should check. From here we can make several more observations. Clearly we're going uphill from the 125 contour to the 150 contour. Where the contour lines are closer together, the land is steeper. Where they are further apart, the land is flatter. These are all basics. Contours allow us to tell where areas are steep and where areas are flat. They also allow us to determine which way a slope is facing. For example, if I was standing here on this slope, I would be viewing broadly eastwards across the landscape, or you could argue I'm looking southeastwards across the landscape, because this slope, going from low to high, is facing in this direction. It's facing broadly east or southeast. This slope has a west-facing aspect because, as you can see, here's the lower end of the slope. The river, always going to be running at the lower end of a slope. Here's the upper end of a slope, and therefore this slope is facing westwards. Knowing the aspect of a slope is really useful because it can explain all sorts of land uses. For example, settlements are often found on aspects which allow them to receive more sunlight. Farmland also could be influenced in the same way. It's notable that when we talk about areas being flat, we really do mean flat. These areas here are flat with only one contour line over maybe a 500 metre stretch. Here you don't really want to use the word flat. This land here is undulating or gentle. So what you're indicating there is it is not tabletop flat. It has some relief, but that relief is not such that it can stop people building things on it. Being able to calculate the percentage steepness of a slope is really, really useful. Before we get to that, let's just recapitulate. What have we covered? We've covered that contours show if it's steep or if it's flat. We've also covered that contours give us actual height value variation in terms of altitude from sea level. We've also covered that contours allow us to show which way a slope is facing, and that's called aspect, and that's really important. Next, we might want to tell the examiner how steep a slope is. Well, the notes are on the screen, so I'm not going to read through them laboriously, but basically what you do is you calculate the run and the rise. Well, let's take this distance here from the 125 contour to the 150 contour. My rise is 25 meters because I'm going from 125 to 150. I can either work that out by doing 150 minus 125, or I can just count up the intervals of the contours. Either way, my rise is 25 meters. Next thing I want to do is I want to measure the horizontal distance I want to measure the horizontal distance from the 125 to the 150 contour. For argument's sake, let's say that that is 10 millimeters. 10 millimeters is 250 meters in reality. So we would do 25, which is our rise, and we would divide it by 250, which is our run, the horizontal distance between the 2 points on the map. You times that by 100 and it gives you a percentage value for the steepness of the slope. In general terms, if anything's over 20%, then it gets a warning sign on if you're driving on the roads. A road over 20% steepness might often have a warning sign saying the road is over 20% steep, and that's something to be careful about. And so that's a good kind of baseline for you to talk about steepness of slope. And if a slope really does look very steep, you can calculate the steepness of it, and you can talk about how that might influence land use. Being able to calculate steepness is useful, so pay attention to these notes, give it a practice yourself, and ask me if you're not sure. So here's a couple of examples. This slope has a rise of 40 and a run of 80. So I do 40 divided by 80 times 100. I get a 50% slope. That's a really steep slope. And consequentially, that's why there's no roads going up it. Or anything built on it for that matter. The slope has a rise of 15 and a rise of 150. Therefore, it's a 10% slope. And that is comfortably within the boundaries of engineering to build roads and settlements, and you can see consequentially over this landscape that exactly that has happened. Okay, here are a few more examples of what you can do with contours. Contours offer you really fantastic opportunities to make observations on the map. For example, in this example, what I've done is I've looked at this area of forest. Maybe I've been asked to describe the distribution of forests. Well, I can say that all of the forests on this map lie above the 250 meter contour. At first that looks confusingly difficult to work out. It's really not that difficult. I just find the highest contour value within the forest area. There it is there. The dot, black dot indicating the top of a hill at 358. And then I can work my way in contour values towards the edge of the forest. And then I need to get to the furthest edge of the forest, and I'm there. And that is at the 250 meter contour line. Really quite straightforward to do once you know how. And it's a nice way of being able to quickly describe where land uses are found. In this instance, contours have affected the landscape in a different way. Many features, specifically man-made constructions like roads and railways and so on, follow the contours. That means to say that they follow the contours. They follow areas of equal height. A contour line, remember, is a line on the map where all the heights are equal. So if I walk along the 180 contour line, I'm always at 180 meters above sea level. I'm never going uphill or downhill. I'm going to go around the hill, but I'm never going to go up or down. So what engineers do is they tend to follow these contour lines. It's obviously easier to construct and to drive along a road that is built following contour lines. Wherever possible, we would try to achieve that. Little note to all advanced R pupils, where I'm referring here in the notes to the road follows the contours of the bluff line. The bluff line is the line at the edge of a floodplain before it heads upslope. So here's a river, here's its floodplain, there's the bluff line, the end of the floodplain, and here's the road built following the contours at the bluff line. River, floodplain, bluff line, road following contours. Here's a wee example for yourself. Test yourself. What are the aspects of A, B and C? Pause the video because I'm about to tell you. The aspect of A is south. The aspect of B is north or northeast. The aspect of C is west. Okay, so things to consider when we look at contours and relief are altitude. How does the height affect temperature, ability to farm, ability to live comfortably? You could use the contours as map evidence to inform those judgments. Aspect. This affects daylight, temperature, and it affects the view. So if you're being asked to comment on the viability of a land use for a certain area, think about how the aspect would affect the view from a hilltop, or the view of a pathway being built across a landscape. Relief, this means the bumpiness of the land, affects the ease of movement and construction of infrastructure. How easily are you going to be able to move across that landscape? How easily are you going to be able to construct whatever it is you're constructing in that landscape? Okay, so that's us at the end of our introductory video. I did say it would be a quick tour, and rightly so, because there's plenty of ground to cover. That said, if you review this video, it does have really important themes within it, specifically about scale. There's really important notes there in how to calculate scales, and also how to use contours properly to be able to manipulate the map to score marks for yourself. Okay, I hope that was useful.